So we will start with we have done the structural isomerism, correct?
Yes, miss.
We have done the structural isomerism completely, linkage, ionization, coordination, and solvate isomerism. Yeah, tell me, Manik.
I should solve it.
Yeah. So we have not done the stereoisomerism. We will start with the stereoisomerism. Okay. So stereoisomerism is there are basically in your syllabus. Okay. There are basically in your syllabus coordination 4 type and coordination 6 type. Is that okay? We don't have any other case. But
Yes, yes.
complexes of different types are available where you can have 5 ligands, 3 ligands, 2 ligands are also possible. Okay. Like for example, the Tollens reagent is AgNH3 twice. So it is just having 2 ligands. Fine. But in our syllabus, we have only 2 types of complexes under this lesson. One is the coordination 4 type complexes. The other one will be coordination 6 type complexes. Okay. Now, when you look at the stereoisomerism, there are 2 types. One is the geometrical, the other one is the optical. The stereoisomerism is possible for coordination 4 type and coordination 6 type. Okay. And under coordination 4 type, there can be square planar and the tetrahedral. Okay, tetrahedral complexes. So you have 4 ligands. The metal can be surrounded on 4 sides by 4 ligands on a single plane, such that all of these atoms lie on the same plane. Fine. Such a structure will be called a square planar. But if
Because
you
then only
have
we can achieve the unique cis and trans ones, right?
yeah,
If I'm not wrong.
yeah.
Yes.
Or else you can have the arrangement in tetrahedral pattern. So when it is coordination 4, you can have 2 types of arrangement, square planar and tetrahedral.
Tetrahedral.
But the geometrical isomerism of this type will be possible only for the square planar type and not for tetrahedral. So we will be studying the geometrical isomerism for coordination 4, but for only square planar and not for tetrahedral. Fine?
Yeah.
So when it is octahedral, when it is coordination number 6, then it is octahedral.
Octahedral.
And if it is octahedral, then there are 2 types of geometrical isomerism. The geometrical isomerism exhibited here is called as cis-trans.
Yeah.
Okay. So, and tetrahedrals do not exhibit the geometrical isomerism. Octahedrals do exhibit. One is the cis-trans, the other one is the facial meridional. The other one is the facial meridional. Okay, coming to stereoisomerism. Stereoisomerism is possible for coming to optical isomerism. Optical isomerism may be possible for all, but we will mainly study for the octahedral. Tetrahedral also it is possible. Square planar also it is square planar not possible. In the optical isomerism regarding the square planar will not be possible. Because there will be a plane of symmetry. So if there is a plane of symmetry, it will not be possible. So
As in like
how
mirror, right? If you put it in a mirror, it should not be identical.
it should not be
Identical. If we put it in front of
identical.
a mirror.
Yeah, it should not be. Yeah. So square planar will have a plane of symmetry. So it will, as you say, it will look identical on the mirror and it is superimposable also. Therefore, it will not. So the coordination 4 type complexes, if you see, the square planar complexes will not show, octahedral and tetrahedral will show. So when you look at the coordination 4, the tetrahedrals will not show the cis and trans. When it is coordination 4, the square planar complexes will not show the optical. Is that okay? Vice versa.
Yes,
Vice versa. Okay. So we'll go for the geometrical isomerism in coordination 4. Then we will go to coordination 6. We'll talk about cis and trans. So in the same order we will start. So we are going to do the cis and trans in square planar, then cis and trans in octahedral, then facial meridional, and then we will go to optical isomerism. Okay, so we'll start with the cis and trans in square planar. So in a square planar structure, the metal is surrounded by 4 ligands having an angle of 90. So you have got ligand, 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 and ligand. Supposing these ligands are of different type. For example, you have got metal has got A is a ligand and B is another ligand. Assume that there are 2 A's and 2 B's. Fine. A complex with 2 A's and 2 B's. That means A and B are the ligands. If you have two identical ligands of same type, the other case will be when it is A2BC. That means what? The metal is surrounded by 3 types of ligands. 2 of them are identical, the other 2 are non-identical to one another. The metal is surrounded by 4 ligands. 2 of them are identical, the other 2 are identical to each other. Fine. 2 A's are AA will be identical, BB will be identical. The other case is when the metal is surrounded by 3 types of ligands, 2 A's and B and C. That means A is identical to A, B and C are non-identical to any one of them. Are we clear?
Yep.
The third case where the cis trans is possible will be when the metal is surrounded by the ligands A, B, C, D. That means if all the 4 ligands are non-identical to one another also, cis and trans is possible. Is that okay? So under these 3 circumstances, cis and trans will be possible. So when you are looking for a complex, what you should see? Supposing I am looking for a complex and I am trying to think whether it is capable of showing the isomerism. Okay, look at this case. The square bracket closes here. Look at this case. Is it not metal A2B2 type? No, it is not that actually. Oxalate is a didentate ligand. So it is A2B2 type, okay. But it is octahedral. Do you realize that it is octahedral, children? Do you realize that it is octahedral?
To be octahedral, 1, 4, 8. I don't think it's octahedral. For octahedral, you need
See.
6, right? There's only one. There's
Yeah, but
Fine.
oxalate
It's
is
only four,
COO
right?
minus and COO minus, no?
Oh, because
So it
it's
is a
C2O4.
didentate.
Okay.
It
The
is
oxygen is 2. Okay.
didentate. So it donates from this side, that side. Similarly, COO minus bonded to
Oh, so then it
COO
becomes
minus.
6.
Cell
Okay.
is octahedral, right?
Yeah. So collectively, it will be called as one ligand, second ligand. But the metal is forming 6 coordinate bonds. So its coordination number is 6 only, right?
Mm.
Yeah. So this is octahedral. The second one is also octahedral. It is ethylene diamine. Ethylene diamine is a didentate ligand. Remember? NH2, CH2, CH2, and NH2. So both the nitrogens can donate the electron pair to the same metal. So having 3 ethylene diamines means the cobalt is receiving 6 electron pairs. So this is also octahedral. Okay. Now think about this. Can we say that this is MA2BC type? MA2BC type?
MA2BC type. Okay, yeah.
Because
Because
there are
2 of them are two are same, and then the other 4 are same.
the other 2 are
Yeah.
different. This is
Here
ammonia
goes 2 times. Yes, miss.
and this is water. Are we clear?
Yep.
Okay, something like PT, sorry, inside the bracket, PT Cl2NH3 twice. Will it not be metal A2B2 type?
B2. Yeah.
Yeah. And supposing we have got platinum, a chlorine, a fluorine, an ammonia, and a water. Then this will become M, A, B, C, and D. 4 different types of ligands. So in such cases, you will see the cis-trans isomerism in 4 coordination compounds. We are not touching the octahedrals now. Here it is octahedral, 5 plus 1.
But miss, if
6.
all 4 are different, then you will not see cis and trans, right?
We will see. That is the condition here. So we'll see here.
How miss? If all four are different, how can there be
Adra,
matching?
we will see. We'll see. Okay, so we will
Okay.
analyze all the three types. Okay, so whenever it is a square planar structure, what we do is the positions around the metal is put as 1, 2, 3, and 4. So it sits on a same plane, right? Like this. A,
Mm.
1, 2, 3, and 4. So can we say that position 1 and 2 are close to one another?
Yes. So that's cis.
So,
Yes,
yeah.
miss.
So we will take the structure and we'll say 1 and 2. Similarly, 2 and 3 are close. These
Oh yeah.
positions, as you said, are cis. So 3 and 4, what about 4 and 1?
4 and 1. 4 and 1 are also cis because they're
Ah.
close to each other.
So those which are not close positions, what are they?
They're trans.
So 1 and
1
one
and
is
1 and the opposite one. So 1 and 3.
yeah, 3 and 2 and
2 and 4.
4. So these are transpositions. Are we clear?
Yes, miss.
Yep.
So supposing you have got metal, 2 ammonias, assume that it is platinum, 2 ammonias and 2 chlorines. Then can we draw the cis and trans structure? Platinum, you can put ammonia and ammonia, chlorine and chlorine. And on the other hand, we can take the platinum and put ammonia, ammonia opposite to one another. Chlorine and chlorine consequently will become opposite to one another. So can we say this is cis and this is trans isomer?
Yes, we can because trans
Yeah.
it's opposite each. They're all opposite
Yeah.
each other. Cis they're
Yeah.
all close to each other. Okay.
Yeah. And what is isomerism? Compounds having same molecular formula but different
But
structure.
different structure.
Yeah. So this compound's formula is this. This compound's formula is also same. But they both are totally different. They both have totally different structure and possibly they will have different colors also. Is that okay? If they have any colors, their colors need not match. They are two independently existing compound having something common among them. They have same chemical formula, but they have got different structures.
Is it
Is that
so the
okay?
different structures can cause different colors?
Yes, it can cause. It can cause.
Okay.
Why no? The coloration is always because of the DD transition, correct?
Mm.
So if a metal is surrounded by the ligands in one pattern, 1, 2, 3, and 4, and if the ligands change their position, 1, 2 here, 3 here, 4 here, then the metal is influenced by the electron cloud in a different way, no? The metal
Oh,
here
so
is
the electron
influenced by the
interaction. Okay.
electron interaction. So what DD transition and what energy absorption happens in the electrons of this metal may not be exactly same for the next one.
Mm.
And hence the absorbed color and the transmitted color would be different. So different arrangement may lead to different colors. In fact, if you can I'll just open the textbook once again. If you can look at the Werner's theory, remember we had two different compounds.
Yeah, we had.
I mean, two compounds having same number of same composition but different colors. See here.
Yeah.
What about this one? Same composition but
they have
different
different
color.
color.
So obviously
Green,
their
violet.
ligand arrangement pattern would have been different. That's why they are giving different colors.
Okay.
Okay, so different arrangement of ligands may land you into different colors also. Okay, so that case is clear. Okay,
Yes,
so
yes.
supposing you have got Ma2Bc type, we can start writing. You can also start writing, and if you have understood. So if supposing we have got a platinum and you have got two ammonias, a chlorine and a fluorine. I'm not taking care of the charges and all, okay? Because we are focusing on learning the isomerism, not about the structure and charges and all. So can we say platinum, ammonia will be, this will be cis,
Okay,
can
so
we say?
cis, yeah.
And if ammonia is here, where it should be? In its
Opposite,
transform.
complete opposite.
So NH3, Cl and S. So this is again, what case is that? MA to BC type. Fine. So this will become cis
Yes.
and this will become trans. The name will
Yeah.
be same. The name of the complex will be same. So if you want to distinguish, then you will attach the word cis and write the complete name. Similarly, for this, you can attach the term trans and write the full. Clear?
Mm.
The cis and trans is the only one which will distinguish the name of this compound from the name of the second compound.
Yes. Miss, do
Okay,
we
coming to
capitalize the C in cis while writing the name?
yeah. It should be. Because the
Okay.
first letter in every name will be capital. Okay.
Okay.
So coming to M, A, B, C, D type. Okay. So let us put the M. Let us put the four groups. Say A, B, C, and D. Fine.
Yeah.
They are all dissimilar to one another. But can we
Yeah.
say that A and B are close to one another?
Yes, miss.
Okay.
Same
So
with C and D.
can we draw one more where A and B are close, but the C and D have exchanged their position? So
Well,
think
this,
about it. Is it different or same case?
no, it's identical.
No, it is not. See, A
Oh,
and
is it
B are
because A and
close.
D and A and C? Oh,
Ah,
okay, okay.
A
The
and D
interaction
are
between A and D
close,
and E, yeah. And now
but
A and D are
Now A
opposite.
and
ah,
D are like far away from each other.
yeah. So this will become cis with respect to AB. Fine.
Yes.
This is also cis with respect to AB. So what will be the third case? Can we put A and B in trans? So this will become C and D. So can we say this is trans with respect to A and B?
Yes.
Look
Okay.
at
So
A and B.
so this is a different this is still geometric, right?
Yeah, all these are geometrical only. Cis and trans.
Oh, okay. It's a different type of cis and trans.
Yeah.
Okay.
And you don't have to write this cis and with respect to not required. Why? Now, if you focus on say A and B, what will you call this? If now we shift our focus from A B to let us say AD, what can you call it?
Cis there in cis.
This will be cis. What is here A and D doing?
Trans.
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 And what
Also,
is
miss,
A
we
and
do have
D?
to write, right? Because now the name
That's
itself is
cis.
changing.
So we can say this is
It's
cis,
trans.
right?
Yeah, that's cis.
Cis. So there will be always two cis and one trans. You don't have to say with respect to what. You don't have to say with respect to what. It is understandable.
Mm.
Understood. So there will be how many? There will be three. What are they? There will be two cis and one trans. M, A, B, C, D type of complex will exhibit cis and trans. Yes. How many isomers are possible? Three isomers are possible. Two of them are cis and one of them is trans. Is that clear?
Yes.
So
Yes,
you
miss.
can now take any of the two ligands as reference. So you don't have to speak about it, I'm saying. You don't have to say, you can take anything. For example, you can take B and C. So with respect to B and C, what is the first one?
With respect to B and C, now first one would be cis, second one
Second
would be
one,
trans, and the last one
trans.
would be cis.
That's all. So there will be always two cis and one trans. Is that okay? So you don't have to say with respect to this, with respect to that and all. So there will be two cis and one trans. Is that okay?
Mm.
Okay. So that
Yeah.
completes the geometrical isomerism with respect to four coordination system. So we have completed this part. Fine. We have
Hmm.
completed this part. Now tetrahedral complexes do not exhibit. Why they don't exhibit is whenever you take a tetrahedral complex, all the ligands are they not identically placed with respect to one another? Is anybody close by? Is anybody far away?
No, I think they should all be 120 degrees apart.
109.5. No,
Oh,
supposing
it's one
methane is
not
taken.
9.5.
Yeah.
I'm not
So
sure with the exact value.
109.5, 109.5, 109.5,
Oh,
10
120 is trigonal planar. Yeah, yeah.
Yeah.
planar.
This is
So every one is as close as the other pair, right?
yeah.
It is equidistant. Each of the ligand is equidistant from the other three. So it is not possible for us to think about, okay, this is close by and this is far away, right? So tetrahedral complexes do not show. If you replace this carbon with the metal and the hydrogens with the ligand, then you can say all the ligands are placed at equidistant positions with respect to one another. So they will ask you why the tetrahedral complexes do not show the cis and trans. You will say the 4 ligands will be equidistant to one another. Therefore, they do not exhibit cis and trans. Is that fine? Taken?
Yes, miss.
Okay. In a tetrahedral complex, all the 4 ligands are equidistant from one another. So they will not exhibit cis and trans
Cis and
isomers.
trans.
So they will ask you this in a why type of question, give reason type of question. Okay, coming to now the octahedral complex. So we will do the octahedral cis and trans. So we are going to work on this again with 6 ligands. So metal is placed at the center and there are 6 ligands. So how are these actually? We'll think of 4 ligands sitting on with the metal on the same plane. One is on top and the other one is in the bottom side. Fine. So if I'm going to put the positions 1, 2, 3, 4, 5, and 6, then which are the groups which are close by? What will be cis positions?
Here, obviously, 3, 4 are cis, 2 and 3 are in cis, 1 and 2 are in cis, 1 and 4 are on cis.
Okay, and don't you think
And
5
and
is
4?
Yeah, 5
5
and
and
3.
4, 5 and 3, 5 and 2, 5 and 1.
Yeah, so 5, 1,
So
2, 3, 4. What about
only
6?
one that's in trans is 6 and 5.
6 with 3, 6 with
Obviously,
4.
6, 3,
Ah.
4, 1, 2.
6 with
So
2.
6 with 1, 2, 3, and 4. So what will be transposition?
5 and 6,
And
2 and 4, and 1 and 3.
yeah, 2 and 4 and 1 and 3. Fine.
Yeah.
So you know now you need 2 identical ligands to exhibit this kind of isomerism, correct?
2, yes, because all the pairs are in 2. Yeah.
So that either they can be placed close by on cis positions or they can be placed in transpositions, right?
So, miss, it can be 2 and 4, like as in not 2 position. What I'm saying is they can be 2 identical ligands and 4 identical ligands.
Yeah.
Or it could
So,
be 2, 2, 2 as well, right?
So Ma2, you are saying B4,
B4.
correct?
And Ma2, B2, C2 is also possible, right?
Yeah, one more is possible.
A2, one more?
B3, C, M, A2, B, C, D, E is also possible. Idea is we want 2 identical
A2.
ligands.
As long as A2 is there, it's possible. Any form is possible,
So
right?
the other 4 can be totally different. 3 can be identical, 1 can be different, 2 can be identical, other 2 can be identical, or all the other 4 can be identical to one another. Is that okay? So
Yes,
this helps us to identify whether it is capable of exhibiting.
Miss, this is trigonal bipyramidal shape, right?
No, octahedral. Why?
Oh,
Is this not octahedral?
No,
Trigonal
the shape name.
Bipyramidal will be this. This will be trigonal because on top it forms a pyramid.
Okay, never mind.
In the bottom side also it will form a pyramid.
Octahedral is one more. Okay.
Octahedral is one more. Okay, so it will be these. So if you have say something like Fe, NH3 twice, then you have got CN4. So this will exhibit, right? I'm not looking for the charges and all, okay? Ideally, if it is +2, this is -4, then there should be -2 charge. So can this exhibit cis and trans?
Yes, miss.
Which one, miss? Yeah, as long as it's A2, yeah.
So you can now devise your own ones. Fe, NH3 twice, Cn twice, H2O, and a Cl. This will be able to exhibit both with respect to ammonia and cyanide, right? Okay. So you know how to identify now?
Yes, miss.
And any more considerations required? Not required, no? Can we say draw the trans form of this complex? What you will do, Fe?
Transform,
the-
we have to move the NH3 to opposite
Ah,
lines.
yeah, NH3, and the rest of the positions can be given to the cyanides.
Or we can put NH in the top and bottom as well.
Yeah,
Or we
yeah,
can
yeah,
change
yes.
from
Yes.
2 and 4 to 1 and 3, anything. So.
Yes, yes. Is that okay?
Yeah.
Yeah.
Okay. Right. Yes, ma. So this part is over. Can we
Yes.
consider
Yes.
this segment over?
Yes, miss.
Okay. Now we are going to octahedral, facial, and meridional. Okay. Octahedral, facial, and meridional. So when you look at an octahedral structure, you see why it is called as octahedral. There are only 6 ligands. It should be starting with the term hex. Why is it oct? Any idea?
Octahedral, miss, 6 ligands,
There,
octahedral because
oct will normally represent 8, na? Octagon.
true. Is it because I had eight planes?
8 phases
Yeah,
of
plane
this.
spaces. Yeah.
Yeah.
That's what I mean.
See, if you imagine,
Top 4, bottom 4.
yeah, there is a square pyramid, right? It is a square pyramid.
Mm.
And the square pyramid will have four phases.
I know 5,
Right?
miss. Square pyramid will
4.
have 5.
4.
No,
Because
square
the
pyramid has 1, 2, 3, 4, and then bottom 1, 5.
yeah, that bottom is now covered up by the lower pyramid. No?
In octahedral it's not 5, but in
Yeah.
normal square pyramid it's
Yeah.
4, 5.
But whenever we have a pyramid sitting on a particular surface, we will say there it has got 4 because it's sitting
because the
on
bottom
the
is on the okay.
yeah. Okay, but in an octahedral structure, there are 8 phases. 4 to be counted from the top and 4 to be counted from the bottom side, correct?
Mm.
So we call it as octahedron, 8 phases. Is that okay?
Mm.
Okay. So now think of this. If metal has got A3, B3, will it exhibit cis and trans?
Metal's got A3, B3. We know compulsory is A2.
Hmm.
So it's possible, but there will be interlock. There will be
No,
one
there
cis.
is a no, there is a possibility where all are cis. For example,
It
and
won't be
A.
trans. All will be cis.
Yeah. Okay, it is possible that this is cis and cis. Possible, right?
Yeah.
Mm.
But instead of calling them as cis, what we can say is the 3 A's are present in such a way that they form one of the 8 phases of the octahedral structure.
Yeah. Yes, but
Okay.
what if you put the A on the other end? That's my question.
So supposing the A is put elsewhere. For example, A is put here, other 2 A's are sitting here. So by joining these 3 A's, do we get the outer face of this octahedral structure?
Yeah,
Do
we
we
do.
get it?
We get a flat
Do we get
one.
flat, but that's passing through the octahedron? Na? This
Mm.
is located
Axial?
in the outermost. No, this is located in the outwards part, correct?
Yeah,
Of a
the
pyramidal
second one is
structure.
axial, right?
No, it will be called as meridional. Why meridional?
Maybe
Because
the-
when you connect the 3, it will actually pass through the octahedral structure. It will cut the octahedron into 2 halves.
Mm.
It will cut the
Oh, okay.
octahedron into 2 halves, right? Upper half and lower half, correct?
Yes, miss.
But if you move your knife along the A, and A, it touches the outermost face and does not cut the octahedral structure, correct? If I'm going to take a knife and I'm going to move along A, then I'm just gliding on the outer surface of this octahedron. But if I move the knife along with all the 3 A's, then I'm going to cut the octahedron into 2 equal halves.
Yes, miss.
Okay, so this will be called as facial because the 3 identical ligands are located on the outer face of the octahedral structure. Whereas this will be called as the meridional because the 3 are able to cut through the octahedral structure. They are able to cut through the octahedral structure. Is that okay?
Yes. Yes, miss.
Okay.
Understood.
Any doubts in this, ma? Anit?
No, miss.
Okay. So the facial meridional needs at least 3 identical. So what are the other options? You can have MA3, B2C, MA3, BCD. Fine. So the first one can exhibit facial meridional. The second one can exhibit two isomerisms. What are they?
The second one can exhibit. Miss, but my question is, why can't we put one A on top and two A's opposite each other?
Where do you want to put?
Miss,
I'll put the
for the second,
positions.
no, Miss,
1, 2, 3,
can you
4,
move the
5, 6.
yes,
Now,
Miss? Can
now
you
tell me.
move the A from 6 to 1?
Okay, if you do so, you are going to get the facial, no?
Yes, ma'am, but if you move A from 3 to 5,
3 to 5. Okay, then it becomes meridional. Now,
also now
join the
it's very
3. Join the 3. Will it not bisect the entire octahedron?
okay. So so basically, if it ever bisects the
Yeah.
octahedral, then it's
Mm.
always meridional. Okay.
Yeah. Yes. Is that okay?
Yes.
Okay. Just give me 1 minute. I'll do. Rubber band it. Finish person. Rubber band it. రెండు rubber band. I need more one. Mm. I think enough. Yeah. Can you see me now? Let's check.
No, Mr. Camera's turned off.
Camera is switched on. Yeah. Can you see me?
Yes,
Yes,
miss.
miss.
Okay, and I'll do one thing. Okay. So you will see this is an octahedral structure. Can you see?
Yes, miss.
Okay, so I've taken just 3 pens. Okay, I've taken 3 pens and I've attached them like this.
Mm-hmm.
Fine, like this. Is that okay? Okay, I have to remove that background effect. If I remove, you'll be able to see. Background, new diagram. Where is none? None is not there. None is not there.
No, miss, there is.
Where is it?
Like you
There
go to your
should
video
be.
settings, background and effects.
Yeah.
No, not there. In the video, in the camera option. Yeah, background effects.
Okay. Yeah, that's what I did. And
You just click what you chose.
oh,
Miss, whatever you've already picked, you need to click again.
You just click that.
okay. Okay.
Yeah.
So now you can see me clearly, right?
Yes, miss.
Okay. Now let us look into this. Okay, you are saying you wanted to have it where you want one here. Okay. I'll just remove this. Otherwise, I will not be able to tell you. So I have one here, and one here. Think about
Yes,
this.
miss.
One, and one. So when I pass my knife like this, will it not bisect the entire molecule into 2 equal halves, this side and
Yes,
that side?
because it's cutting into the octahedral.
Yeah. Similarly, if I have it one here, and one here.
So we're cutting it horizontally.
Yeah, 1, 2, and 3. Then I'm going to cut it horizontally into 2. But supposing I have the ligands, one located here and the two more located here and here, then it's going to form an outer face of this octahedral structure, correct?
Yes.
It's going to form an outer face of an octahedral structure. So the three identical ligands forming the face of an octahedral structure will make the facial isomer, and any of the other positions where the three are not able to form a face will make up a meridional isomerism. Is that okay? So
Yes.
for example,
Yes,
I
miss.
have got the ligands located here. 1, 2, and 3. 1, 2, and 3. So when I connect them, it will form a face. Yeah, one
Yes.
is
So
this, the
if
second
it
is,
it forms a face of the pyramid,
yeah,
it's facial.
yeah.
And if it is slicing it horizontally or
Or
vertically,
vertically,
then it's
then it will
meridional.
become a meridian. Is that okay?
Yes.
Okay, right. Okay, then, so facial meridional is okay. Now tell me the second one. It is able to exhibit two geometrical isomerisms. In octahedrals, there are only two. What are they? It could be cis and trans, it could be facial meridional. So check whether the middle one can exhibit cis and trans also.
Middle one.
Hmm. There are two identical
A3.
ligands, no?
Yeah, it can do the same. There's no difference.
So it can exhibit cis trans. And
And
since there are,
facial.
and facial meridional.
Yes, you can do all four.
Is that okay?
Yeah.
Is that okay? But the first one will exhibit.
The first one only exhibit
What's the
facial and
cis?
meridional.
Cis, right?
Huh.
Oh yeah, facial and meridian. Sorry, not cis.
The last one will also exhibit facial meridional, but not cis and trans.
Yeah.
So it is based on our requirement only, no?
Yes, miss.
Is that okay?
Mm.
So did
Yeah.
we not select this MA2B3C? So MA2B3C will exhibit both cis and trans and facial meridional. Cis and trans due to two identical A's, and facial meridional because of three identical B's.
Yes, miss.
Is that okay?
Yeah.
Clear? Okay. Let us now go to what is left out. We have the optical. Okay. So under optical, one case is very clear. If it is tetrahedral, see this under optical tetrahedral cases will have, supposing you've got ammonia, you've got chlorine, you've got fluorine, and you've got water. In carbon compounds, you would have studied, no? You have not studied so far. Optical isomerism, you have not studied, right?
Mm-hmm.
You have not heard of the term optical activity, etc., right?
No, miss. No, not yet.
Okay. Okay. So this compound, so let me give you some background about what is optical activity. Okay. Shall we?
Yes,
Okay.
miss.
So what is optical activity? First of all, we will understand the term. If a compound is optically active, if a compound
Compound
is
is
optically active, then if you take that compound in the form of a solution, if you take the compound in the
solution.
form of a solution, okay, that means you have
Okay.
to
As it
dissolve it in a
dissolving?
solvent. Yeah, by
Okay.
dissolving it in a suitable solvent. And then you need to pass a beam of light, which is plane polarized light. So we have to understand
Plane
what is meant by plane polarized light. Shall we?
Okay, miss.
Okay. So when light is traveling, you can still see me, right?
Yes, miss.
Yes, miss.
Supposing the light is propagating. Light propagates in a straight line, right?
Mm.
Okay. So when light travels in a straight line, we know light is electromagnetic radiation. There is an electrical component and a magnetic component. The electrical component is like this, right?
Yeah.
And the magnetic component is exactly perpendicular to this plane. Fine. So if you treat this to be the path of the light, then the electrical component is located on the XY plane.
Mm.
But the magnetic component is located on the XZ plane.
Oh, yes, they're perpendicular to each other. Yeah.
Yeah, perpendicular to each other. If the pencil here represents the plane containing electrical component, then the magnetic component is like this. Is that okay?
Yes, miss.
Okay. So I can ignore if I'm going to take the magnetic component as reference or electrical component as reference, anything is fine because anything is okay. So let me take the electrical component. So can I say that the electrical component is lying on this plane?
Yes, it is.
In this plane. For this light ray called A, the electrical component lies on the XY plane. Is that okay?
Yes, true.
Okay. So there can be another light ray which may have a slightly turned orientation of the electrical component.
Mm.
So corresponding to that plane, but the perpendicular plane will have the magnetic component. That's why I said you monitor any one. So for the first ray, the electrical component was like this, oriented on XY plane. But for the next ray that I am speaking of, the electrical component is slightly rotated.
Mm.
Yes, miss.
For a third one, the electrical component can be further like this. Perpendicular to that will be the magnetic component. So how many such possibilities are there for the electrical component?
Possibilities
how
of
many-
electrical component. It has infinite, right?
Infinite possibilities. So if I'm going to look at the ray traveling towards you or towards me, can I say that this is how the electrical component of this ray will look like?
Mm. It'll be
For
a
the
perfect line. Yeah.
the second one, it may be slightly tilted.
So basically, it'll change for every case.
Yeah, change for every case, right? So there are infinite possibilities. So the light which is coming to your eyes, I'm going to draw this only now. I'm going to draw this only. So if you are a viewer here, the electrical component can be located like this, or can be like this, or can be like this, can be like this, and so on, right?
Mm.
Okay, different light rays will have orientation of the electrical component in different planes, infinite. So their electrical components or their magnetic components can be located on any of the planes, right? Many planes are possible. So such a light, so is it consisting of one ray or many rays? What light is coming to you if you are
It's
sitting
many
here?
rays.
Many rays.
So you are getting many rays, and each one of them have got electrical component oriented in its own way it likes. Such a light is said to be circularly polarized light.
Mm.
Okay. Now what I'm going to do is I'm going to place a filter, a fine filter. And I'm going to allow all these to pass through that slit. It's called as a slit.
Mm.
So can we say that the rest of it is opaque?
Yeah, only a small amount of light will pass through.
Yeah.
Okay.
So all this is opaque. Only this, the inner rectangle, no? That is only allowing the light. The rest of it is a cardboard, I assume. It's opaque. So the light which is going to escape this slit alone will come out, isn't it? So think of this. Let us say this alone comes out. The rest of it will be held back, right?
Yes,
Right?
miss.
Okay. So now what you have got is said to be the plane polarized light. So a circularly
So that's
polarized
plain
light is a
polarized
mixture of radiations.
Okay, miss.
Mixture of electromagnetic radiations having the electrical component oriented in any of the axis any of the plane. But so you could have placed your slit like this also. You could have placed your slit like this also. In that case, the light whose electrical component is like this only will come out. Is that okay? The rest all will be held back, filtered off. So you are getting plane polarized light. So what is plane polarized light? Plane polarized light is a light which has got the electrical component lying in one single plane. It can be many rays, but all of them lie having their electrical component on one single plane. Clear?
Mm.
So this light is passed through. This light is used up here. So I'm going to put it back. So I'm going to use that. So this line represents the orientation of the electrical component of the light. Any problem with this?
No.
No, miss.
Now, if the compound is so this story is not required anymore. Okay, this story is not required. So if the compound is optically active, let us take another compound which is optically inactive. Okay, the light is passing. Just give me a minute. Okay, so supposing the compound is optically inactive. So they have taken two situations. One is the plane polarized light is passed through optically active solution. Optically active compound solution. And another plane polarized light is passed through a solution which contains optically inactive substance. So when the light emerges out, it would have turned by some angle.
Mm.
If the
Returned, but because of the solution. Okay.
I'll tell you, if it turns, the compound is said to be optically active. But if it is optically inactive, the light emerges without any rotation.
Okay. Understood.
Understood? Understood?
Yes, miss.
Okay. Manit, is it okay?
Yes, miss.
Okay. So if a compound is showing optical isomerism, we'll go back. If the compound is showing optical isomerism, that means two different compounds. One compound showing rotation in clockwise direction, its isomer should show rotation in anti-clockwise direction to the same extent. If compound
Mm.
A and B are optical isomers, then
Mm.
if compound A rotates the light to plus 13 degrees, the compound B should rotate the light to minus 13 degrees. So the two compounds have same chemical composition, formula is same. Okay, different spatial arrangement. And show different optical rotation. How different? Can one show plus 13, another show plus 23? No. Since the two compounds are optical isomers of each other, they should be able to show optical rotation to same extent but in opposite direction. If this is plus 23, this has to be minus 23. Clear?
Yes, miss.
Only then, okay, how will we identify? The compound A will look like the mirror image of B. The compound A will look like mirror image of B. Fine?
Mm.
The compound A will look like mirror image of B. Second condition, the compound A, when drawn on a paper or as a whole, if the molecule is lifted and is brought and made to sit on top of B, it should be non-superimposable. Okay, all this idea of the non-superimposability, the term enantiomer, we have to talk about that and all this is more relevant when we come to the haloalkanes and haloarenes. We will talk about enantiomers we will talk about the optical isomers. Currently, you just have to understand that compound A and B can be called as optically active if they are able to rotate the plane of the polarized light. If compound A is rotating by plus 23 or plus 30, its isomer will exhibit rotation in the exactly opposite angle. So they will have same chemical composition, different spatial arrangement, one showing, let us say, optical rotation in positive side, other one will
On
show
negative
rotation
side.
in opposite to the same magnitude. Okay, so what kind of compounds will show? Okay, how do you know that they are optically active? But there is only one check. What is that? There should be no plane of symmetry. Lack of plane of symmetry. If there is no plane of symmetry, then the compound is optically active. This is the only thing we can do it on the paper. Whether it rotates or not, it is an experimental thing. Is that okay?
Yes, miss.
Yes,
Is
miss.
that okay? So what you can do, if you want to check whether there is optical activity for the compound or not, you go and check whether it has a plane of symmetry. If it has a plane of symmetry, it is not optically active, it is not optical isomer. But if it is not having a plane of symmetry, then it is an optically active substance. It is optical isomer. So if it is an optical isomer, its mirror image will be its isomer. So we'll take up one case, fine, to understand
Hmm.
this. And the rest of the case we'll take up in the next class. There
Okay,
are
miss.
only 2-3 cases. Okay. So that is why, supposing a metal is surrounded by 4 different ligands, ligand 1, ligand 2, ligand 3, ligand 4, there is no plane of symmetry. There is no plane of
No
symmetry.
penis. Okay.
But supposing this is L2, then there is a plane of symmetry.
Mm.
Then there is a
So
plane of symmetry. Is there,
we okay. So we created. Okay, understood.
see, metal, ligand 1, ligand 2. You take that plane and cut through the molecule. Cut through. Take a
Hmm.
knife and slice. So you're going to
Okay.
slice like this. Will the knife not
Yes,
pass through this point?
it will.
If your
Will.
if your knife is touching L1, M and L4, then the knife will pass through this. This side L2, that side L2. The back side will have L2, front side will have L2. So there is a plane of symmetry, no? The two equal halves. Molecule is cut into two equal halves. The front side will have L2, back side will have L2, front side will have L2.
Mm.
What if this is L3? Then there is no plane of symmetry. No matter how you cut, you can't cut it into two identical halves. Is that okay?
Yes, miss. Yes.
If so,
Yes.
then its mirror image is its isomer. L1, L4, L2, and L3. So these two will be now the optical isomers. They are two independently existing molecule, children. They are two independently existing molecule having something in common. What is that? They both have same chemical composition, but they have different spatial arrangement of groups. And they look like mirror image forms of one another. If this person stands in front of the mirror, there will be left-right inversion, isn't it?
Yes. So that's
So
why this
what?
is optical isomer.
So if this rotates by plus 49, then this has to rotate by minus 49,
Hmm.
provided the composition is same.
Understood.
Up to this, is it okay? So tetrahedrals
Yes,
with
miss.
four non-identical ligands will definitely exhibit optical activity. But the question is not about tetrahedral here. The question is about octahedral. So is it okay if I continue? But it will go on for next 5 minutes.
It's okay.
It's okay, miss.
It's okay, okay. Supposing you've got metal and I've got 6 positions in an octahedral structure. Fine.
Yes.
Yes, miss.
Okay. Now supposing I have got a chlorine here, and ethylene diamine. Ethylene diamine is NH2, CH2, CH2, NH2. Okay. Why to go to that first? Let us take this as fluoride, bromide, cyanide, and ammonia. Is there a plane of symmetry in this molecule?
In this molecule already, no, not yet.
Check
Oh
again.
yes, yes, there's we can see obviously see chlorine and chlorine opposite to each other.
Yeah. So if I take this octahedral structure and cut through like this, ammonia will be sliced into upper half and lower half. Cyanide will be
Mm-hmm.
sliced, fluorine will be sliced, bromine will be sliced. On top, you see chlorine, in the bottom, also chlorine. So is it not going to be cut into two equal halves?
Yes, it will. So it will
So
just
It
like
this
will.
this.
has plane of symmetry. So will it exhibit optical isomerism?
It should not.
Yeah. What is the
Mm.
primary condition for optical
It should not.
isomerism?
It should
It
not
should
have
not
a
have a
plane of
plane of
symmetry.
symmetry.
Should not.
Supposing this is something like iodine. Now check.
Then yes, of course, it can show optical
So
isomerism.
it does not have a plane of symmetry. So it will exhibit optical activity. So where is its optical isomer? Its mirror
Mm.
image is its optical isomer. So cyanide will be seen on its cyanide was on the right, comes to left. Not comes to left, it appears to be on the left. Cl and I. So this is assuming that this is rotating the light on the positive side. This will rotate on the negative side. The one which rotates on the right side is often is called as dextro, and the other one will be called as levo. It's also represented with plus and minus.
Okay, dextro
Okay.
levo.
Now,
Okay.
by looking at the molecule, you never know which is dextro, which is levo. It is purely experimental detail.
Mm.
Okay. Now, coming to another case, metal has got Cl and Cl. I've got ethylene diamine, NH2, CH2, CH2, NH2. So I'm going to put it like this, just for the sake of simplicity. Like this. Is that okay?
Okay. Miss.
So can we imagine that the ethylene diamine is located here and here? So what is the formula of this complex? It is MCl2En twice. Is that okay?
Mm.
Okay, this curved line represents the entire ethylene diamine, which is a didentate ligand. Does this have a plane of symmetry?
Does this have plane of symmetry? Yes, it does have plane of symmetry.
Yes, and again the same, no? This plane.
Same logic as before.
Okay, ethylene diamine will be sliced into half, upper half, lower half. On top, chlorine in the bottom. Supposing this is bromine, does it have a plane of symmetry? Think about it and tell me.
Now, yes, it still does.
Where is it?
Through the center, the chlorine and bromine line.
Through the chlorines. Like this, if you cut this side ethylene diamine, that side. Can we cut like this also?
Yes.
Yes. Half of the ethylene diamine on this side, half of the ethylene diamine on that side. Clear?
Yeah.
Okay. So I'm going to come back. Can this complex show cis and trans isomerism?
Can it show cis and trans? This one has given. Technically, it should be able to because there's two ethylene diamines.
No, it's not about ethylene diamines. It's
But
about the
miss, we know that if
chlorines.
no, miss, but there's only one chlorine, so it should not be able to show anything.
There are two chlorines I changed.
Miss, oh, you changed it back. Okay, yes,
Yeah.
then it should be able to show.
Is that okay?
Yes, miss.
Is this the cis form? Can I say this is cis form? And this is the trans
Cis.
form?
Yes, because they're close and they're far. Yeah.
Yes,
The two
yes.
chlorines are close chlorine. Okay. The trans has a plane of symmetry, you told, right? Does the cis have a plane of symmetry?
Cis have a plane of symmetry in this case. Trans is yes. Cis cut. No, there's no plane of symmetry.
There is no, because this is protruded towards you, this is inwards, and this is on the plane.
Mm.
Okay. So do you think you can cut the molecule into two equal halves?
No.
No. So no plane of symmetry. So optically active. There is a plane of symmetry. So not optically active. So if it is optically active, then where is its isomer? Put the mirror and draw
Just
its
put a
mirror
mirror, I
image.
put dextro and levo.
Hmm. So now your this thing will be here, and the two chlorines will be sitting here. Lateral inversion, left, right. So did they change? Did it change? No. These are two different molecules. Actually, there are three different molecules occurring in the universe. Two of them are cis, and these two are optical isomers, optically active. One has to be dextro, the other one has to be levo. Is that okay? And the
Yeah.
third one, the trans is optically inactive. Is that okay?
Yes, miss.
Okay,
Hmm.
right? So there is
Yes,
one
miss.
more, just one more case, which is metal. If you have got three ethylene diamines, then also it is optically active because there is no plane of symmetry. You can't think of bisecting the molecule like this. Fine.
Hmm.
Don't imagine that. Why? Because
Because
this
it's
is
not possible.
inwards, this is outwards, this is outwards, this is on the plane. So diagrammatically, it looks like that. But they are totally, if you bisect it, okay, you don't find a group similar to this on the right side. So they are not. Okay. So that will be here, here, and here. So this is again, they both have, so something like, say, chromium En thrice, okay, with positive 3, will exhibit optical isomerism. One is cis, sorry, not cis, sorry, they're not cis. So the one of them will be dextro, the other one will be levo.
Hmm.
Is it clear?
Yes, miss.
Yes, yes.
Okay, so go through the optical isomerism, geometry, I mean the stereoisomerism, and see if anything else is left out. Okay, so I think I've
Yes,
covered
miss.
almost all. Next class, we will start with the optical activity.
Okay, miss. Thank you, miss.
So this much is there, the optical isomerism and this much. This much. So we had to speak so much, but in your textbook, it is condensed.
Hmm.
Okay, right. Okay, so next will be, we'll meet on Thursday, right?
Yeah.
Yes,
Okay.
miss.
Yes. Okay.